the last talk of the afternoon session, and we'll hear from on proper time oscillation.
My name is Hao. I'm from San Francisco. So the topic I'm talking today in the presentation is related to the concept of proper time in the matter field. So let's take a look at a few fundamental questions. Now, in relativity, we know that time and space are treated on an equal footing. But in quantum field theory, of course, time is a parameter. It cannot be treated as an operator. In fact, Pauli actually even suggests that time cannot be treated as a self-adjoint operator because if it forms a conjugate momentum with the Hamiltonian, the Hamiltonian is for a typical system is bounded from below and also this way. So ends up time is not treated as an operator. No, in addition, when we look at quantum theory, we look at a quantum harmonic oscillator, it has oscillation only in space. So if time and space are to be treated on the same footing, can there be also oscillation in time? Now, more interestingly, if we look at bosonic field, in the bosonic field, an oscillator, it has a very similar formulation as the quantum harmonic oscillation. So, because of the formulation, can there be some relationship between time and space with that oscillation? And so that's the starting point of our analysis. We make one assumption. We assume that matter can also oscillate in time and see what kind of properties we can get. Now, if this assumption has any merits, it should be giving us the properties that we predict from quantum theory and also relativity. So that's what I want to try to demonstrate in this talk. We find out that we can reconcile the same property of a non-interact spin-zero bosonic field from a matter field that has oscillation in time. And we'll have to explain what do I mean by oscillation in time, because it's a concept that is new. And if you are a particle physicist, you'll be concerned. The standard model is very accurate. If you modify how time is propagating, not a parameter in the theory, you may be generating some properties that are not that does not conform with the theory and also with the experiment. I will demonstrate to you that there is no such conflict until the effects of the time oscillation we can detect. And we haven't reached that level yet, but we are getting close. There are other properties that we can generate from the matter field with oscillation time, and it will reduce the difference between the quantum theory and also general relativity, such as the internal time of this matter field can be treated as a self-adjoint operator. We can also develop a proper time or uncertainty relation that are similar to the position and momentum uncertainty. Most interestingly, we look at how the proper time oscillation can affect the surrounding space-time geometry. Without using the Einstein field equation, just look at the oscillation in time at one point and see how the space-time curvature will look like. We find out that the field is a Schwarzschild field around the proper time oscillation. So, finally, we will demonstrate that there could be some experimental proof that may help to verify whether there can be such an oscillation. And that includes the neutrino time of arrival and also the decay time of a muon. So that's the main reason why I come to this conference, because with all the expertise in the experiment, time of arrival and also time measurement, I hope I can get some feedback on that as well. So this is a list of paper peer-reviewed and published recently, but all the information that is generated in this talk actually comes from these papers. It's spread all over the place, so I have recently drafted the paper and summarized everything. Now, let us explain what do I mean by oscillation in time. And we take an analogy in here. Now, equation 1 in here, this is very simple. we consider a particle that has motion only in space. It is traveling with a velocity v in here, but with oscillation. So we now have a particle traveling, and then but it oscillates. So this is motions in space. Now, think about it, if the oscillation, the frequency is very fast and the amplitude is very small. If the instrument is not sensitive enough to detect this oscillation, this particle will still travel along a smooth projection. So you won't see the oscillation if your instrument is not sensitive enough to do that. Now, so if there is if time and space are supposed to be treated on the same footing, let's replace this oscillation by time. And in equation 2 in here, you can see that this t here is a coordinate time, which we will adopt this for convenience right now. But when we do the gravity, we'll have to make everything relative. So there's no such thing as a fixed coordinate time in relativity. And then we have an oscillation, but now all emotions are in time and space. So this is what I mean by oscillation in time in here. So same thing, if the instrument is not sensitive enough, we will still see that this particle will propagate along time along a smooth time-like geodesic. Now this plot here demonstrated the concept. And this is the only assumption that we make in our analysis. The purple line in here is the smooth time-like geodesic we learned from relativity. Now we have oscillation in time. So you can see the time rate actually picks up and then slows down. And then it flattens out, and then so it keeps oscillating up and down. But we never go back to the time in the past. So we avoid the dilemma that there will be time traveling. So this is the only assumption. So if matter has this oscillation, what kind of properties we can get? Now we can extend this oscillation to a matter field. And this is simple. I mean, this wave here is just the matter oscillating in time. There's no oscillation in the spatial direction. Now, in another reference frame, observed, moving at a velocity relative to the reference frame we have before, you see that there will be oscillation in time and also in space. And this we are calling theta tk and theta xk. It is a Lorentz covariant plane wave that we can written in here. So it can be applied to a relativistic theory. Now we can define further a plane wave here in theta k, and such that the time and oscillation displacements are the derivative of theta k relative to time and also in space. Now one thing is interesting is theta k in here satisfy the time Gaussian equation. So theta k actually describes the dynamics of the matter field, and then the derivative of theta k describes the displacement in time and space as well. Now let's take a look at a system that in the volume V with multiple particles with mass m, and the Hamiltonian density is very simple. We can get it easily from there. Now, the first property I want to demonstrate to you is that this matter field, the proper time has to be quantized. Now, if we look at a wave that has only oscillation in time, the Hamiltonian density in here, if you look at that, it's corresponding to a harmonic oscillator, like the spatial oscillation. But now we have oscillation in time. Now, think about the matter inside the box. If it has oscillation in time, it doesn't have oscillation in space. This energy has to be an intrinsic energy. But this matter field we are considering has no charge and is free. So what kind of energy we still have inside this system? The only energy we have is the mass energy. So this energy here, the H0, must correspond to the mass energy of the particle inside the box. Now, if there are n number of particles, the Hamiltonian density will have to be equal to the mass energy times the number of particles in here. We can equate the energy of the oscillator with the number of particle energy of the number of particles And there is a quantization condition in here. Now, n is the number of particles. Since n is discrete, these proper time oscillator must be quantized. And so this field, the proper time matter field with proper time oscillation, must be a quantized field. We have to quantize this system. There's no classical continuous distribution of time in here. Now, the second property wants to demonstrate to you is that the matter field has the same properties of the bosonic field. Now, we can easily superpose zeta k and its conjugate momentum to form a free real scalar field in here. As we have demonstrated earlier, it needs to be quantized. And by looking at the new real scalar field, we can relate directly with psi x in here from quantum field theory, the bosonic field. And it has a direct relation with it. But now we can write the annihilation and also the creation operators in terms of the proper time oscillation. So the oscillation in time actually generates the mass energy of the particle. Now think about that. E equals to mc squared. It may be oversimplified to think about that m equals to c squared. It looks like the energy of an oscillator. C is a rate of time if we make that interpretation. So E equals to mc squared looks like something that could be an oscillator. But I have to emphasize that it is oversimplified. We cannot think of it this way because we're looking at a quantum system in here. Now, so the particle that we will observe in this bosonic field actually is a particle that has oscillation with amplitude T0 equals to 1 over omega 0. And omega 0, if we look at that as the Bloch-Wheeler internal energy, for electron, this is 10 to the power 21. So the amplitude of this oscillation is very small. So if our instrument is not sensitive enough to detect that, this particle will still travel along a smooth timeline to distance until the effect of this oscillation can be observed. Now, the second properties I want to demonstrate to you is that the internal time can be treated as a self-adjoint operator. Now, let's look at the conjugate momentum of the scalar field, zeta. And eta in here is conjugate momentum, which is very straightforward. We can get it easily from our analysis. Zeta and its conjugate momentum will satisfy an equal time commutational relation like this. Now, but if we look at the displaced time of the system, the displaced time and the eta, the conjugate momentum, actually has a direct relationship. So for the displacement time and the real scalar field actually also form a conjugate pair and satisfy a similar commutation relation. But if you remember, the conjugate momentum, the zeta, the bosonic field, they are all self-adjoint operators. So as a TD, the time displacement in here is also a self-adjoint operators as well. And since zeta TD does not form a conjugate momentum with Hamiltonian, it doesn't have a conflict with what Pauli has suggested, that even the Hamiltonian is bounded, or the TD in here will still be a self-adjoint operator. So now let us look at the internal time of the matter field. The internal time actually is a summation of the coordinate time plus the oscillation in time Td in here. But T is a parameter, and Td is a self-adjoint operator. So ends up the internal time of this matter field is also a self-adjoint operator. Now the next one I want to demonstrate to you is that we can obtain a proper time uncertainty relation that is similar to the position momentum and uncertainty relation. Now, let's look at a matter field with oscillation only in proper time in here. And we can obtain the displacement time and also its displacement time rate in here very easily with the same analysis we have. The Hamiltonian density, you can see that how similar this is. That looks like they are quantum harmonic oscillators. except now all the motions are in time and not in space. And PD in here has served as a role of momentum in here. So this whole thing here looks like the quantum harmonic oscillator, but it is oscillating in time. Comparing the properties of the proper time oscillator and also the quantum harmonic oscillator, you can see the similarity. The Hamiltonian, they look the same, almost the same. Commutation relation almost looks like the same. And also the uncertainty relationship, they all look like the same. So this could have an explanation of why the formulation of an oscillator in the bosonic field looks very similar to the quantum harmonic oscillator. And this is just a guess, this is an assumption I made, but this is the assumption we have made to show that there could be some possibility, that there could be oscillation in time. Now, most interestingly, we look at the space-time geometry around the space-time oscillator. Now, if we neglect all the quantum effects, assuming the oscillator actually is stationary and it's a classical object, how does this proper time oscillation at a point affect the surrounding space-time? And we will do that without using the Einstein field equation and see how this curvature is. You can see that a proper time oscillator, at that point, the space-time geometry is different from the space-time geometry at spatial infinity. Because of these differences, you will curve around the space-time around this proper time oscillation. Now, a proper time oscillator is a wave, it's a pulse. Technically, we can Fourier decompose the wave with plane waves. And we can use a Lorentz covariant plane wave, such as like in this kind of form, which has theta tk describes the oscillation in time, and then theta xk described in the spatial oscillation. But if we use theta tk in here to carry out the decomposition of the proper time oscillation, remember theta tk is only a zero component of the plane wave. There is also a spatial component, theta xk in here. So ends up, if we carry out the Fourier decomposition in time, there will be there will be associated oscillation also in space. Now, so after we carry out the analysis, this is oscillation in time that we will expect. Okay. So I'm not going to, and what I want to show you is that we can obtain a Schwarzschild field solution just like what we predict, and the mass here is related to the radius of the shell, thin shell, and also the amplitude of the thin shell. Now, the most important part of here is to look at the neutrino's oscillation, time of arrival. Remember, for a particle that travels in a plane wave that has an average velocity, say, of v, it also will have oscillation in space as well. And this oscillation, we find out that it can be written in a form like this, in terms of the energy and also or the mass of the particle. And this uncertainty, if we look at the propagation, if we're doing an experiment on the neutrino, such an uncertainty could be observed if the assumption is varied. And since the uncertainty depends on the mass, if later on we can come up with the mass of the neutrino in a later experiment, and if we confirm that we have such an uncertainty and also with a similar mass, then it may show some kind of proof that there could be some oscillation in time. Now, there's already experiments on doing the neutrino arrival time, and we hear that in the news all the time. And in the quantum gravity phenomenology, they predict that the uncertainty, similar uncertainty that we have described here, is proportional to e to the power n. But however, n is unknown, and it has to be predicted by, it has to be established by experiments, and also with theoretical prediction. But in here, the theory actually established that n is equal to 1/2. So if we find out later on from the experiment that it is proportional to e to the power 1/2, it will give some vindication of the theory. And later on, if the mass of the, and also from this uncertainty, we can predict the mass of the neutrino. And if it can conform with another experiment that has a similar mass, then it may give us more credibility. So another thing that we can look at is the muon decay. Because if we have oscillation in proper type, it will also have an uncertainty of the proper type for the decay rate. But however, the oscillation, what that requires is, even with an energy of 1 TeV in this case here, uncertainty is 10 to the power minus 22 seconds. So by trying to observe the proper time oscillation, actually I don't think we will have much chance in my lifetime that can be seen. So, but however, if we use neutrino, and in this case I think we're approaching that energy level of 1 TeV in this case. And in the ice cube experiment recently, it is reported that they can even observe 1 PeV in that case. And so, but however, the challenge is neutrino is very difficult to observe. And to collect so many neutrino would be a difficult task. But I believe that there is a possibility. So that concludes my talk. I'm sorry I overestimate my time. I'm maybe talking too slow and I can't catch up.
We have time for a couple of questions, and there is also a discussion time. Do we have any questions already?
Is that kind of off? Why oscillation per se? I mean, maybe I misunderstood, but what's special about periodic or harmonic motion? I mean, it seems to me that the idea of this kind of motion in time is kind of new. So why not? Can one consider other kinds of motion that are not periodic or not harmonic or?
Well, harmonic oscillator. The main reason is the bosonic field oscillator. It's very similar to the quantum harmonic oscillator. So the starting is, can that be oscillation in time? That's an assumption that we make. And so we look at, hey, if we have oscillation in time, what can we get? And we find out that there is a list of results that we can get from there. So the main key thing is we find that there is no deviation from what is predicted by the quantum field theory and also from the relativity, because we haven't reached the energy level of detecting the oscillation in time and space. And as demonstrated, the muon decay, we're far from able to observe any effects at all. But for neutrino, we are getting closer. So that's the motivation why we look at the harmonic oscillator, and rather than any other kind of oscillation as well. It's a new theory. You can see that all the papers that is developed is only within the recent years, and all these are spread over the place. Every paper has one section of what I talk about. So it's never summarized and never, but now it's up to a point that can be summarized and combine them together. Hopefully it makes sense to people, and hopefully from experiment it may provide some kind of verification of that.
Maybe I'll ask one very quick, and then there are more questions. Going to the rest. So just, I'm curious about your choice of neutrino. Was it relevant for picking the neutrino, the fact that they seem to be produced in superposition of mass states? Was it important for the choice? Can you say a bit more about this or clarify?
We actually, the arrival of the neutrino has the smallest mass, the lightest mass we know nowadays. And so, as we can see, the uncertainty of that arrival time actually is inversely, it's not inversely, but in here, the mass actually is inversely, the uncertainty is inversely proportional to the mass. So the lighter the mass of the particle, the easier it can be detected. And so that's why I picked the neutrino to do that. And there is also already experiments with time of arrival for neutrino. But the problem is, right now, the uncertainty that can be obtained, my understanding is only up to like 10 to the power -9 seconds. And what we will need, even if we project the neutrino to very high energy, we're looking at 10 to the power -12 seconds or something like that. So we are approaching that state with neutrino, but I don't think it is too far, because even people doing the quantum gravity, they predict that there could be a chance to observe uncertainty for the neutrino arrival with 1 TeV neutrinos. But of course, it's difficult to collect neutrino in this case. And also this will supplement what the quantum gravity phenomenology that is saying, because they do not know delta T, they do not know the exact theoretical or formula for that. But now with this assumption, we come up with a solution that is equals to e to the power 1/2. So hopefully there's a chance. I mean, if after the uncertainty is resolved, if it is 1/2, then it may give some. Just a try. I mean.
Okay.
Thank you for the talk. So if I've understood correctly, then the amplitude of these oscillations in time is the inversely related obviously related to the mass of the particle, which is a lighter particle than the target oscillations. But if the oscillations become too large, then now you're moving backwards in time to reaching causality. So does this imply a lower limit on mass?
No, it actually never goes back in time. The whole oscillation never goes back in time. Let me go back. You can see that from the assumption. You can see that the oscillation that I have, the assumption is it will flat out. It never goes back in time. So it doesn't. I mean, yeah. I'm not sure if I have already answered this question.
So you're varying both the amplitude of the oscillations and the frequency, I guess.
Yeah, the amplitude is inversely proportional to the frequency. So imagine electron is 10 to the power 21 second, then this amplitude of oscillation is extremely small. So that's why we're saying that the property generated by this matter field will predict exactly the same what quantum field theory and general relativity is saying, until you can detect such a small time interval. But if we project the property of the particle at high energy, this will increase, and this is the chance that the amplitude will increase. So the higher energy of this particle as we go, then there may be a chance to observe these kind of oscillations, and then also the uncertainty.